Hello all, as we continue our investigation into circular functions. In our previous video we looked at what is the unit circle and how can we measure angles in degrees and radians. We're now moving on and we're going to look at the definitions of sine, cos and tan. Now, you may already have some definitions of sine, cos and tan in your head, especially sort of from year 9 trigonometry, dealing with triangles, and we're going to use those below. And the way you've actually been taught sine, cos and tan is in reverse to how they were developed or how they were defined, and I'll get into that more in a second. But we know sine theta is equal to opposite over hypotenuse. We have that mnemonic SOHCAHTOA, okay, where sine is equal to opposite over hypotenuse, cos is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent. We can fill these in. Cos theta is equal to adjacent over hypotenuse. Now, using this triangle here on the right that's inside our unit circle, and we have some point P on it with coordinates x, y, so we have this distance along here as x, that distance up there as y. Using those, let's actually now fill this in. So we said sine theta is equal to opposite over hypotenuse. So opposite in our case to our angle is y. Y is the opposite side. So we get y on the hypotenuse, which is 1. So y divided by 1 is just y. Now cos theta is equal to adjacent hypotenuse. So the side adjacent to our angle is x. So we get x on 1, which just happens to be x. Now if we take those, we can do tan theta is equal to opposite on adjacent, which is equal to y on x, which also happens to be the same as sine theta divided by cos theta. But the big takeaway here more at the moment is these two. Okay? That inside the unit circle, okay, if I have any angle, okay, for some angle theta, okay, sine theta is equal to the y component of that radius. Okay? And this is inside a unit circle, just for a unit circle where it has a radius of 1. So it doesn't matter where I put my line, okay, and I can use the blue one I have at the moment. Go to there, sine theta, so for that angle, sine theta means this distance here, that y component. And that's what I mean by component, is the, I guess, the vertical distance of that line. Okay. Same thing, I could draw my angle all the way over here. I've gone all the way around to that point. Okay. What is sine theta of that point? Well, sine theta by this is the y component. So if I know my y coordinate there, or the y component, or the vertical component, that is what sine is. And it's the flip for cos. Cos is defined as, well, the x value of that line. So if I want to define cos theta of this angle, I would need to look at what is my x coordinate, or the x component. And that's actually how sine theta and cos theta were developed. Mathematicians didn't say, oh, it's going to be opposite over hypotenuse and adjacent over hypotenuse. It actually started with these circles, doing unit circles and saying, right, if I draw a line in there, and it was to do when Greeks were trying to solve this problem of if they had any circle and then they drew a line through it, they were trying to figure out how long this bit was between it. They were trying to figure out, okay, it doesn't matter where I draw that line through, trying to figure out. And so they decided to simplify it down to, well, can we do some work with angles, because they'd figured out pi and whatnot, and they were simplifying. Instead of going the whole line, we're like, well, if we can find half of it, so if we split the circle in half, and they got to this situation like, right, we're going to define that distance there. From now on, we're going to call that sine of whatever angle generated it. and that's where it came from. And then this SOHCAHTOA stuff, or sine theta equals opposite over hypotenuse, was a development on top of that. We didn't start with SOHCAHTOA. Just want to make that really clear. So sine is defined as, we draw any radius inside a unit circle. Sine theta is the vertical component of that line. We have our vertical component, and then we have a horizontal component. So if I had to draw that line instead by going across then up, that would be my sine and my cos components. That's where the definition comes from. And that's going to be really important to think about as well. That's what it's defined as. You can then track trends. So as we follow this graph going round, watching is, let's just think of the vertical component at the moment. Well, it starts really small there, it's getting bigger, and we can see the vertical component here in the middle. Well, that has to be 1 because it's a unit circle, it's gone all the way up to 1, and right here at the end it would have 0 vertical component. Now it's going up, getting big, now it's getting smaller, and it gets back to 0 over here. Now what happens in the bottom half of the circle? Well, same thing, it starts small, gets bigger, gets bigger. Okay. The thing to note is this is going down, and what's special about our y-coordinate down here is, well, that is negative. The y, the vertical component, is negative, and same, okay, it starts to get smaller, going down towards 0 again. The y component, the vertical component, is still negative. So sine is positive, and we call these quadrants, this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. We can see that sine is positive in 1 and 2 because, well, our line's going up. Its y value is positive. And then in quadrants 3 and 4, it is negative. We could do the exact same look, and I'll take those out, for the x component. So it's a little bit harder to see because the line's drawn on the x-axis. The x component's always drawn there. But we can see as it sweeps around, it's all the way across. The x component would be that big, then the x component would be that big, the x component would be that big, shrinking down until the x component, as my line's going straight up and down, it has no x component, so it's 0 there. Then it gets bigger, gets bigger. So over here, at the right hand side, this x component is going all the way across. It's 1, and it's going down, getting smaller and smaller and smaller. Now it gets bigger and bigger coming this way, but what do we notice about x coordinates on this side of the graph? Well, they must be negative. So over here in quadrant 1, going to the right, all my x values are positive. Going to the left, they are negative, so it's getting down to -1. And then it gets again smaller and smaller and smaller, the x component, down to 0, and then it gets bigger again, going back towards 1. And same thing down here in quadrant 3, my x component's negative because the x coordinate is negative. In quadrant 4, the x components are positive because the x coordinates are positive. So that's, if we're thinking physically about where these lines are in the circle, and then we think physically what is my x coordinate or my y coordinate at that point, we can know if it's positive or negative. Okay. That sums up everything I've talked about. Sine is only the y value, cos is only the x value. It doesn't matter where you draw that angle at, sine is your y value, cos is your x value. And if you can think like that, if you can think physically about the circle, visualize where that line is, and then at least roughly visualize what your x and y values are, you're going to always avoid making silly mistakes, or you can make quick error checks of your answers. So let's have a go at this. Estimate the length of sine, cos, and tan in the following to 2 decimal places. So this is just a unit circle, and we're going to make an estimate by looking at, well, how big is the x, how big is the y. So coming across to over here, if that there is 1, 0.5 is probably about there. So that's looking about, I'd say like maybe like 0.70. Make an estimate. And that is looking pretty much the same coming down this way. Half is there is about 0.5. That almost looks that sort of same again. I'm going to say 0.70. Now tan is, if we go all the way back, is y on x, opposite over adjacent. So we would get for this one, it's 0.7 divided by 0.7, which happens to be 1. So we're going to say that's roughly our estimates. Now you could put in that this angle is drawn as negative 45 degrees, put that in your calculator and you can actually find out what the sine cos are. But just by visualizing and going, well, the whole way, the whole distance is 1, the radius is 1, let's break it down from there. So let's go over here for this angle. And let's start with our y component. And coming across, there is 1. I'd say half is about there, so to me that looks about 0.4. So sine is 0.4. And I've just realized I made an error on the previous one. Naughty me. Y coordinate. That should be, the y value should be negative. That should be negative 1. Yeah? Because it's down here. You can clearly see our y coordinate at that point is negative. Same with this first one. What's our y component? Well, our y component is positive. What is our x component? Well, coming all the way across to there is 1. There is obviously about probably 0.9. I'm going to say that's roughly 0.9. 0, and being an x coordinate is all the way to the left, so that needs to be negative clearly, and then I can do this as 0.40 divided by 0.90, again a negative in there, so we get 0.4 divided by 0.9, which we can simplify to 4 on 9. We might just leave it like that for now. The whole point of this though is thinking, where's the dot? What would be the x coordinate at that dot? What would be the y coordinate at that dot? And that's our sine and cos values. Thinking about that, we can then, for a bunch of these at 90 and 180 degree intervals, they're actually, you don't need a calculator to ever do them. If we just draw a little picture and think logically about it. Okay, cos of 90. So if I go around 90, I am there. Cos is asking for the x coordinate. What's the x coordinate of the point going straight up? It's nothing. It's 0. Where our line's going straight up. It hasn't gone left or right, so the x value is nothing. Let's that out. Same thing again. And doing these, it's handy to draw. Actually, let's do that. We'll draw little pictures. Okay. Little unit circles for every single one. I'm going to 180 degrees, so my line is over here. Sine is asking for the y component. What's the y coordinate at that dot? That again equals 0. Cos of 360. Okay, so 360 degrees is going all the way around. So my line is over here. Cos wants the x coordinate. Well, the x coordinate going straight across for a unit circle with a radius of 1 is equal to 1. And we can do that over and over and over. So this. Okay. And the way when we're dealing with radians is to remember that pi is the same as going around 180 degrees, or half a loop. So if you go around pi, you can think about how many loops am I going around, or how many half a times, or 2 pi's gets me all the way around. How many times am I going around the circle? So 3 pi, well, 1 pi gets me to there, another pi gets me to there, another pi gets me around. So my line is out here. Cos wants the x coordinate at that point, while the x coordinate over there would be negative 1. 5 pi on 2, so 5 on 2 is the same as 2.5. So this is effectively saying 2.5 pi. So I'm going 2.5 pi times around. So 1 pi gets me to there, another pi gets to me there, and then I need to go another half a pi. Half a pi is 90 degrees, gets me to there. So that's my point there. Now I want cos, so I want the x coordinate at that point. How far left or right am I? Well, I am 0, so that equals 0. 11 pi on 2, that is the same as 5.5 pi. So let's put, I'm going to need some space for this one. So I'm going around 5.5 times, so there's 1, there's 2, there's 3, there's 4, there's 5, and then another half of a pi. Takes me to there, so that's my line and sine, so I want the y coordinate. It is quite obvious the y coordinate at that point would be -1. Okie dokie. -7 pi on 2. Now -7 on 2, that's the same as -3.5 pi. There we go. So -3.5. So I'm going the opposite direction because it's negative. So there's 1 pi, there's 2 pi, there's 3 pi, there's another half a pi. So my line is straight up and down. I want sine, so I want the y coordinate. So that is going to be equal to 1. Rightio. Cos of -22 pi. This is where we need to start thinking about how can we simplify this down? How can we think about instead of having to count how many times I'm going around, I don't want to count going around 22 times. What I can realize is going around a full loop is 2 pi. So can I write this equation in terms of 2 pi? So I could write this as cos of, and we'll make it 2 pi. What can I write that as? Times how many? Well, that's 11. So I'm actually just going around and round and round and round in circle 11 times. So if I'm going around and round in circle 11 times, I get back to my starting point. So my line is still just straight across. I'm wanting cos, so I want my x coordinate at that point. So that is going to be equal to, and that was -11, but it doesn't matter. We're just going around and round 11 times. We're still back to the start. The x value at that point is 1. Now 991 pi, how can we write that in terms of 2 pi? So we want to write 991 pi as the same as something times by 2 pi. Well, half of 990, if I halve 990, that's going to be 445. So 445 times by 2 pi gets me to 990, then plus another pi. 991 pi is the same as 445 by 2 pi plus another pi. So I'm just going to go round and round in circle 445 times, and then I'm just going to go another pi. So I've just gone one more pi around to there. That means my line is across here. And I want sine, so that's my y component. What's the y coordinate over there at the left? That is just equal to 0. So that's how we can do those. Anyone that falls on the 90 degree or the 180 degree, the 0, or even around at down here, those ones we can just figure out logically. Don't need to put them in our calculator at all. Really quickly, I'm going to have to split this exercise into 2 videos, is how the definitions of sine and cos, they're geometric definitions. It's draw a line inside a circle, measure the vertical component of it, that is defined as sine. Measure the horizontal component of it, that is measured of cos. It's geometric, it's coming from a geometric picture. Tan is technically also the same thing. Okay? It is, if we kept, there's 2 different ways we can draw it in. There's this way, which is commonly shown. So if we had our radius of 1, if we kept drawing that up until it hit a vertical line drawn up from the edge of the circle on the right or the left. However far this distance up here is, however far that distance there, that is called tan. The other way we can think of it, instead of having to continue the line up and then draw a vertical line up at the side, instead is tan is short for, guess what word? Tangent. We can actually draw a tangent at where the radius is. We draw the tangent in all the way to the x-axis. That line there is also our tan of the angle. Those two, that one there and that one vertically up, those two are both of the same length. I like to think of it as the actual tangent, that one, because it's going to help think about what happens as my angle changes. How long is that tangent to the x-axis? And you could also measure it. It's much easier to just rule in a tangent line and then measure it out. So let's think about tangent of 15 degrees. We've got this tangent of probably about, we've got this 60 degrees already drawn in. Let's think about a tangent of maybe 85 and then a tangent of 90. And let's actually think about how big they'll be. So let's draw in maybe 15 degrees. Go to there. I draw a tangent in to that point, just touches, hit the x-axis, that distance there. Okay, so that's pretty small. Okay, so tangent of a small angle is small. As I go up to the 60 degrees, as I already showed, draw the tangent in, across there. That's getting sort of big. Okay, we'll just call it medium for now. What happens if I do tan of 85 degrees? So instead I draw my radius in here, that's about 85 degrees. Now I need to draw my tangent into that point. What do you notice? I would have to keep going on and off across the page. It's actually really big. It's massive. It's large. Okay, that line to keep going until I hit the x-axis is really quite big. And it's going to be bigger than 1, yeah? Much bigger than the radius. If the radius is 1, then that line is many times longer than the radius. And then the last case, the really special case, is what happens if tan of 90? Tan of 90. So if I draw a radius up at 90 degrees and draw the tangent in, what happens? That line is never going to hit the x-axis. Just doesn't happen. So technically, if it never hits, it's undefined. So this is where we get this idea that tan 90 degrees is undefined. Because the geometric line, this tangent line, never hits the x-axis. And tangent is defined as how long the line is until it hits the x-axis. It never does, so it can't be defined at that point. So that's where it comes from. The last useful one here is tan of 45. Let me do some erasing, neaten up this picture. And once I show you, it should make sense why tan of 45 is 1. If I come up, there we go. And that's at 45 degrees. That's 1. Tangent coming down here. And my 45 is probably a bit off, let's be honest. It's probably about there. Okay. Draw my tangent across. That happens to turn into, that's 45 degrees, and since it's a triangle, that must be also 45 degrees. That means if that side there is 1, that side there is 1. It's not equilateral, it is a, I've just lost the name of a triangle with two sides the same length. Scalene. It's a scalene triangle. Left and right. The radius is 1, the tan is 1, because if it's 45 degrees on the left, it must be 45 degrees on the right. Work out as a triangle because the tangent is always at 90 degrees. So that's how tan is defined. Let's see what's on the next slide. So the next slide is the same thing, just finding tan values by thinking logically. Draw a little picture. Tan 45 to there. That must be equal to 1. Tan 405. Well, that would be the same as 360 plus 45. So I go all the way around once, and then I go another 45. Tangent we know at 45 is equal to 1. 10, 9, 90. Well, that's 360 plus 360 is 720. Plus, what's that going to be equal to? 990 take away 720. Oh, it's 180. Okay. So we'd go round a full time twice, and then we're going to go round again another 180. So we're over at the left-hand side. How long is the tangent over there? Well, the tangent is 0, so that's equal to 0. Same thing here, negative 2 pi. We're going to go round one whole time, back to the start. How long's the tangent over there? That's equal to 0. 7 pi on 2, that's that 3.5 pi. So we're going around 3.5 pi times. So that's 1, 2, 3.5 down to here. How long's the tangent down there? Well, tangent's going to go across that way, so it's undefined. And tan of 11 pi, well, that's the same as 2 pi plus, that's 5 by 2 pi plus pi, so that would be going round and round in a circle 5 times, because 2 pi is one circle, go around 5 times, go around another pi. That gets me out to here. How long's the tangent there? The tangent there is equal to 0. Okay. And I will leave it there for now. We'll come back with another video for the remainder of 6b. I hope that helps. If you have any questions, put them in the comments below, put them on Google Classroom, send me an email, or ask in class. Have a good day.